Welcome to InfoSec Bytes, your go-to podcast for bite-sized insights on information security, AI, cloud, quantum, and cybersecurity incident root cause analysis.
It is so good to be here.
With over 100 episodes, we've got you covered on the latest trends and tips. This year, we will focus more on cloud computing along with other topics, so stay tuned.
And I have to say, today's topic is one I am particularly excited about.
Please like, subscribe, and share to join the conversation on various platforms. We're on Spotify, Apple Podcasts, YouTube, Amazon Music, and stay secure.
It's one of those things that I think a lot of people just take for granted, even seasoned professionals.
Or plumbing, right.
It is the plumbing, but it is so much more than just plumbing. It's probably one of the most intense, high-stakes engineering battles happening anywhere in tech right now.
I completely agree. You know, I was spending my weekend just buried in the research stack we have for today. And believe me, it is a stack.
Yeah.
And it stopped feeling like I was reading about server maintenance.
Right.
It felt more like I was reading battle plans for an invisible war.
That's a great way to put it. A war being fought inside the silicon.
Yeah, inside the machines that run, well, pretty much everything, the entire internet.
It's a war for isolation. It's a war for performance. And ultimately, it's a war for trust.
So that's our mission for this deep dive. We're going right into the trenches of the battle of the hypervisors. We're focusing on the big three. So that's AWS, Azure, and Google Cloud. And we're going to try and answer a question that I think is really fundamental, but we often just gloss over it.
What is that question?
How do you take one single physical server, a box of metal and silicon, and slice it up into tiny, secure pieces for thousands of different customers?
Multi-tenancy.
Yeah.
The magic trick of the cloud.
It is a magic trick. How do you keep them all completely isolated so, customer A can't spy on customer B?
And just as important, how do you make them all feel like they have the whole machine to themselves?
Exactly. If I'm a major bank, I don't want to feel like I'm sharing a bunk bed with a startup's gaming server.
No, you definitely do not. And that's the core conflict, the central tension of the entire cloud computing model.
It's what makes the economics work.
Absolutely. If we had to give every single customer their own physical server, the cloud would be, 10, 100 times more expensive. It'd be completely unaffordable for most.
So this trick is everything.
It is. But as we're going to see, the way these three giants pull off that trick has changed so dramatically. I mean, we're talking about a complete paradigm shift over the last decade.
It used to be all software, right?
All software.
Yeah.
Now it's about custom-designed silicon, specialized hardware, and basically rewriting the fundamental rules of how operating systems interact with hardware.
And just to set the stage for you, our listener, I want to be upfront about where this is all coming from. The research we're pulling from today is, it's dense.
It's not light reading.
Not at all. We're talking about deep technical white papers from AWS, really detailed security design documents from Google, blog posts from Microsoft's core infrastructure engineers, architectural reviews.
We've gone through the footnotes, the appendices, the stuff that makes your eyes glaze over.
So you don't have to, but we need to talk about why you should care. You might be sitting there thinking, okay, this is neat, but I just deploy containers, or I'm a CISO, I manage policy. Why does the hypervisor matter to me?
And the reason is trust. It all comes back to trust. If the hypervisor fails, the entire cloud model fails.
It's the foundation.
It's the foundation. If there is a single crack in that foundation of isolation, then the wall between your data and your competitor's data, it just vanishes.
So this isn't just an implementation detail. This is the core architecture of trust for the modern internet.
That's it.
It's like buying a bank vault. You don't just care that the door looks heavy. You need to understand the mechanism of the lock.
A perfect analogy. You need to know how it works because your security depends on it.
Okay, so let's unpack this lock. Before we get into all the shiny new technology, the nitro, the titanium, all of that, we have to look back. We need to set the scene. How did we used to do this? What was the old world of virtualization?
Right. So let's hop in our metaphorical time machine and go back to, say, the early 2010s, the dawn of the cloud as we know it.
Okay.
Back then, the industry was almost entirely reliant on software virtualization. And you'll probably recognize some of the names. We're talking about S or some of the early implementations of KVM.
And Exen was the big one for AWS at the start, wasn't it? I remember that was what everyone talked about.
It was. It was the de facto industry standard for a long time. And in that model, the main physical CPU in the server was, it was doing double duty, maybe even triple duty.
It was overworked.
It was the hardest working component in the entire data center by a mile. It had to run the customer's applications. That's the workload you're actually paying for, right?
Right, my code.
But on top of that, it also had to manage all the infrastructure. It was processing network packets, managing every single storage I/O request, enforcing security rules, switching traffic between VMs.
Okay, let me try an analogy here because that sounds really complex.
Go, Kerr.
The CPU is like the CEO of a company.
I like it, yes.
The CEO is supposed to be focusing on high-level strategy, running the business, which is my application.
The value-add work.
Exactly. But in this old model, the CEO is also stuck answering the phones, sorting the mail, unclogging the toilet in the break room, and checking visitor badges at the front desk.
That is a perfect, perfect analogy. And what happens when the CEO is doing all those little chores?
They're not getting any strategy done.
Precisely.
Yeah.
This created what the industry calls the virtualization tax. Because the CPU was constantly being interrupted to do all this housekeeping, a significant chunk of its power was just lost. It was overhead.
How much are we talking?
It varied, but sometimes 10, 20, even up to 30% of the CPU cycles were just being consumed by the hypervisor itself.
Wow. So I'm paying for a top-of-the-line processor, but I'm only getting 70% of its actual power.
You were paying for the CEO, but you were getting a part-time receptionist. And this led directly to another huge problem that I'm sure a lot of our listeners who were early cloud adopters will remember with pain.
The noisy neighbor problem.
The noisy neighbor. It was the bane of the early cloud. Because the central CPU was the bottleneck for everything. If one customer on the server decided to do something really intensive,
like run a massive database query that just hammered the disk I/O.
Exactly. Then the central CPU would get completely bogged down just trying to manage all that storage traffic for that one customer.
And that means everyone else on that physical server slows down.
Everyone. The CEO is so busy dealing with one angry, screaming client on the phone that nobody else can get a word in.
So my e-commerce website might suddenly load slower because some guy 3 virtual partitions over decided to start mining Bitcoin.
That's exactly what it meant. And the worst part was you would never know why. You'd look at your instance's metrics and your CPU usage would look fine, but everything would be sluggish because the underlying physical hardware was completely choked.
That's infuriating. Now, what about the security side of this? The performance tax is bad, but security is where this gets really scary for me. I remember reading about something called DOM0 in Excel.
DOM0.
It just sounds ominous, like a villain's secret lair.
It was certainly a massive, massive target for attackers.
Yeah.
In the SN architecture, you had this special privileged virtual machine called Domain 0, or DOM0.
And what did it do?
It was essentially a full Linux operating system running on the bare metal, right alongside all the customer VMs, but it had God mode access. It had root on everything.
So it managed the network drivers, the storage drivers.
Everything. All the I/O for every other VM on that box passed through DOM0.
Okay, so let me connect the dots here. If I'm a hacker and my one goal is to cause maximum damage, and I somehow managed to break into DOM0.
You own the box. Game over.
Not just my VM.
No. You own every virtual machine running on that physical server. You can read their memory, you can steal their data, you can shut them down. It was the ultimate single point of failure.
And it was a full operating system with the shell and libraries and utilities.
Yes. Which means it was a huge, bloated attack surface.
Yeah.
All the complexity of a full Linux distribution sitting right there in the most critical, privileged part of the system. If you could find any vulnerability in any of those components and compromise the management layer, you'd won.
So let's recap the old world. We have a performance tax stealing our CPU cycles. We have noisy neighbors making our apps unpredictable. And we have a giant glowing security target in DOM0. It sounded like the whole thing was kind of a house of cards.
It was a necessary stepping stone to get the cloud off the ground, but yes, it was fragile. It wasn't going to scale to where the industry needed to go.
Which brings us to the new paradigm. Something had to change. What was the big shift?
The big shift was a realization across the industry. All 3 providers, AWS, Azure, and Google, they all came to the same conclusion, more or less independently.
Which was?
They couldn't keep scaling like this. They had to stop making the main CPU do all the chores.
So, sticking with our analogy, the CEO finally decided to hire a proper office staff.
Exactly. They hired a receptionist, a mailroom clerk, a security guard, a whole team of hyper-specialized, incredibly efficient assistants.
And in technical terms, that means moving the infrastructure work off the main CPU.
And onto custom silicon.
Yeah.
Onto specialized hardware.
This is often called the system on chip or SoC revolution, right? Or people talk about SmartNICs.
That's right. SmartNICs intelligent network interface cards are a huge part of this. The goal became this kind of holy grail. bare metal performance with virtualization security.
You want the customer to feel like they are running on raw, dedicated hardware.
But with all the flexibility, security, and management benefits of being in the cloud, you get the best of both worlds.
Okay, so let's dive into the first giant who really went all in on this new paradigm. Let's talk about AWS. They seem to have been the pioneers with something they call the Nitro system.
Yes, AWS really led the charge on this specific architectural shift. The work started way back, maybe 2012, 2013, but it really started hitting the market in a big way around 2017, 2018.
And the research points to a key moment. It wasn't just a software project.
No, this is a bit of business history that completely shaped the future of tech infrastructure. Amazon went out and acquired a company called Annapurna Labs.
I've heard that name. They're an Israeli chip design company, right?
They are. And this is so important. AWS didn't just buy a software company or hire more kernel developers. They bought a world-class chip maker, specifically to build custom silicon for their data centers.
So they brought the hardware design in-house.
Completely in-house.
Yeah.
This was the move that allowed them to start systematically dismantling that old software-heavy X model we were just talking about and replace it piece by piece with their own hardware.
So what does the Nitro system actually look like? The research we read breaks it down into 3 pillars. I think we need to go through these one by one because this really feels like the blueprint that everyone else had to respond to.
It absolutely is. So if you can, visualize a server motherboard. Normally you just think, okay, there's a CPU, there's RAM. Nitro fundamentally changes the anatomy of that server. The first pillar is the Nitro cards.
And these are actual physical cards, like a graphics card that you plug into the motherboard?
Similar form factor, yes, but for a totally different purpose. These are highly specialized I/O cards. There isn't just one Nitro card, there's a whole family of them.
Okay, what do they do?
There's a Nitro card for VPC networking. There's a separate Nitro card for EBS block storage. There's one for instance storage, this super fast local NVMe drives. And then there's a master Nitro controller card that orchestrates the whole thing.
Hold on a second. So you're telling me that when my EC2 instance saves a file to an EBS volume, my main CPU, the Intel or AMD chip that I'm paying for by the hour, it isn't actually processing that storage request?
That is correct. And this is the magic of the system. The main CPU just says, hey, Nitro card, please write this data to this volume, and then it completely forgets about it.
So the Nitro card handles it all?
The Nitro card has its own dedicated processor, its own RAM, its own encryption engine, its own logic. It handles the data encryption, the network routing to the EDS backend, the I/O scheduling, everything. The main CPU is completely free to just keep running your code.
That's how they get rid of the virtualization tax.
Completely. The tax is gone. And it also solves the noisy neighbor problem.
How so?
Because all the network and storage limits, the quality of service rules, they're enforced in hardware on the Nitro card itself. So if your neighbor tries to flood the network with 1 billion packets, the Nitro card on their instance simply drops the excess packets before they ever even get near the shared network fabric or the main CPU. It creates a hard physical barrier.
That is a much more robust solution. Now, the second pillar, this is where, for me as someone focused on security, it gets really, really interesting. The Nitro security chip. The research calls this the hardware root of trust. What does that mean in plain English?
Okay, let's think about the boot process of a server. It's the most vulnerable moment. How do you know that the low-level firmware, the BIOS, hasn't been infected with a rootkit before the machine even starts up?
Right. If the foundation is compromised, everything you build on top of it is worthless.
Exactly. In a traditional server, the main CPU is what loads that firmware from a flash chip on the motherboard. If that firmware is malicious, the CPU is compromised from the very first instruction it executes. It's like waking up inside a dream that has already been hacked by someone else.
That is a genuinely terrifying thought for an infrastructure operator.
It is. So the Nitro security chip is a small, dedicated security processor that physically sits on the motherboard between the main CPU and that flash storage where the firmware lives.
It's a gatekeeper.
It's an incorruptible gatekeeper. It physically traps all I/O, all read and write requests to that non-volatile storage. When the system boots, the very first thing that happens is the security chip powers on, and it cryptographically validates every single byte of the firmware before the main processor is even allowed to see it.
So the main processor, the one running my workload, it literally cannot write to the firmware, even if it's compromised.
It is physically impossible. The research from AWS states they literally cut the write-enable traces on the motherboard that would go to the main CPU. The only thing that can authorize a firmware update is the master Nitro controller, and that only happens via a secure, authenticated, and logged API call from the AWS control plane.
So even if I'm an attacker and I get root access on the instance, and then I find some zero-day and break out of the VM onto the host, I still can't flash the BIOS.
You still can't. It eliminates an entire class of attacks known as bootkits, or persistent firmware malware. It's an incredible security guarantee.
That is incredibly robust. Okay, so that brings us to the third pillar, the Nitro hypervisor. But I have to ask, if the hardware cards are doing all the networking and all the storage, what is actually left for the hypervisor to do?
And that is the absolute genius of the entire Nitro architecture. Because all of that heavy, complex, and dangerous lifting has been offloaded to the dedicated hardware cards, the hypervisor doesn't need to be a full operating system anymore.
It doesn't need network drivers?
Nope. The hardware does that.
Doesn't need storage drivers or a file system?
Nope. The hardware does that too.
So it gets to go on a diet.
A massive, massive diet. A traditional hypervisor like XN or a full-fat KVM might have millions of lines of code. The Nitro hypervisor is a heavily stripped-down, lightweight version of KVM. That is, depending on the version, somewhere in the ballpark of 50,000 to 100,000 lines of code.
Wait. From millions of lines of code down to 50,000? That's not a diet. That's like going from the entire encyclopedia down to a single pamphlet.
It is a radical reduction, and it essentially does only two things. It manages memory allocation between VMs, and it schedules CPU time for the VMs. That is it.
So it just carves up the RAM and the CPU cores.
That's all. It's what we call a quiescent hypervisor. For the most part, it just sits there and stays completely out of the data path. And from a security perspective, this is a monumental win.
Because less code means fewer bugs.
And fewer bugs means fewer potential security vulnerabilities. You've shrunk the attack surface by an order of magnitude.
There's a phrase in the AWS research that I found really, really striking, and I want to unpack it. The phrase is no operator access.
Yes. This is core to the philosophy.
Because I think most of us, even professionals, have this lingering assumption that if we put our data in the cloud, somewhere there's a sysadmin at Amazon or Google who could, in an emergency, log into the physical server and see what's going on.
Yeah, that is precisely the assumption that the Nitro architecture is designed to destroy. The core design philosophy is that there is no mechanism for a human operator to log into a production Nitro host.
What do you mean, no mechanism?
There is no SSH daemon listening. There is no root user account with a password. There is no interactive shell. There is no admin login for AWS employees.
So if a hard drive fails or the machine is acting weird, a human being can't just log in and poke around to see what's wrong.
Exactly. The system is designed to be managed entirely by a control plane via APIs.
Yeah.
It only accepts authenticated API calls for specific, limited actions. Commands like attach this EBS volume or reboot this instance.
But there's no command for dump the memory of that customer's VM or read the raw blocks of that customer's disk.
There is not. The system is designed with a passive API. There is no functionality that would allow an operator to access customer data.
That's an incredibly bold claim to make. I mean, software has bugs. Code can be flawed. How do they actually prove that the system enforces this? How do they know there isn't some hidden loophole?
This is where they go beyond standard software testing. They use a technique called formal verification.
I've heard that term. Is that just like super advanced automated testing?
It's much, much more rigorous than testing. Testing is like running your code through a bunch of scenarios to see if it breaks. Formal verification is about using mathematical logic to prove the correctness of your code's logic.
So it's not just checking for bugs, it's proving their absence.
In a sense, yes. They use a system called TLA+ to model their boot code and their authorization logic. They don't just test that an unauthorized operator can't access memory. They create a mathematical proof that the system can never, under any circumstances, enter a state where such an access would be permitted.
So it's the difference between test driving a car to see if the brakes work in a few situations and using the laws of physics and engineering to prove that the brakes must work under all conditions.
That's a great way to think about it. It provides an incredibly high level of assurance, which is critical for customers with high security or sensitive workloads.
That is mind-blowing. Now, before we leave AWS, we absolutely have to talk about Firecracker. The research brings this up in the context of serverless computing, things like Lambda and Fargate. Why did they need a whole new virtualization technology just for that?
Well, think about the performance profile of a Lambda function. You trigger an event, the code needs to spin up, run for maybe a couple hundred milliseconds, and then immediately die.
It's ephemeral.
Extremely ephemeral. And traditional VMs, even the super fast Nitro-based ones, take a second or two to boot up. That's an eternity in the serverless world. It's just too slow for functions as a service.
Okay, so VMs are too slow. What about containers? Like Docker, aren't they fast?
Containers are very fast to start, yes, but they have a different problem.
Hmm.
Security. All containers on a host share the same Linux kernel.
Ah, the shared kernel problem.
Right. If you're running thousands of different functions from thousands of different customers on a single machine, a shared kernel is a security nightmare. If one customer finds a way to crash the kernel, everyone on that machine goes down with them.
Or worse, if they find a kernel exploit, they could escape the container and attack the other customers on the same host.
And that's a multi-tenant security breach of the highest order. So they needed something with the speed of containers but the security isolation of VMs.
So Firecracker is the middle ground between those two.
It's designed to be the best of both worlds. Firecracker is a completely open-source virtual machine monitor, or VMM, and it's written in Rust.
Rust. We keep hearing about that language in the context of secure systems. Why is that?
It's all about memory safety. Rust's compiler provides guarantees that make entire categories of bugs, like buffer overflows and use-after-free errors, impossible by design. These are the types of bugs that have plagued systems written in C and C++ for decades.
So it's a safer foundation. And what does Firecracker create? Not full VMs, right?
It creates what AWS calls micro VMs.
And how micro are we talking here?
We are talking incredibly tiny. A Firecracker micro VM can boot in about 125 milliseconds.
125 milliseconds.
Sure.
That's literally faster than the blink of an eye.
It is. And its memory overhead is less than 5 megabytes per VM.
That's nothing. So you can pack thousands of these onto a single server. How does it achieve that speed and density?
By being aggressively, ruthlessly minimalist, a Firecracker micro VM has a very, very simple device model. It only knows how to emulate 5 devices: a network card, a block storage device, a vSock for communication, a serial console for logs, and a keyboard controller to signal a reset. That is it.
So it doesn't know what a USB drive is. It doesn't know what a sound card is. It has no idea about legacy hardware.
None of that complexity exists. And as we said before, less complexity means a smaller attack surface. But they don't stop there.
There's another layer.
There's another layer. They use a component called the jailer. The jailer is a second line of defense that sandboxes the Firecracker process itself. It uses standard Linux kernel features like coup groups and sitcom filters to create a tight little box around the micro VM.
So even if an attacker finds a 0-day in Firecracker and manages to break out of the micro VM,
They're still not on the host. They're trapped inside this second outer jail with almost no permission to do anything. It's defense in depth, implemented beautifully.
incredible. Okay, so AWS has gone deep down this rabbit hole of custom silicon, minimalist software, and memory-safe languages. But they are definitely not the only players in this game. Let's pivot. Let's talk about Google Cloud.
Google, the engineer's engineer.
Right. The research we looked at highlights GCP's approach with hardened KVM and their own silicon projects called Titanium. How does their philosophy differ from what we just heard about from AWS?
Well, there are a lot of similarities at a high level. Like AWS now, Google uses KVM, the kernel-based virtual machine that's part of Linux, as their foundation. But the research from Google is very, very specific about one phrase.
And that is?
Not QEMU. They emphasize this over and over.
And QEMU, just to remind everyone, is the standard user space program that's used with KVM in most Linux distributions, right? It does the hardware emulation.
Oh, it is. It's the industry standard. But from Google's perspective, QEMU is, well, it's a huge, sprawling, ancient code base. It has drivers for everything under the sun, including legacy floppy disk controllers and ancient sound cards.
Things you would never need in a cloud environment.
Never. And Google looked at that complexity and said, this is too big of an attack surface. This is too dangerous. They specifically referenced a famous vulnerability called Venom.
Oh, I remember Venom. That was a big one.
It was a nasty VM escape vulnerability that was traced back to a bug in QEMU's virtual floppy disk controller.
A floppy disk driver vulnerability taking down a modern cloud server. The irony is just, it's painful.
And terrifying. So Google's reaction was, why do we even have a floppy disk driver in our cloud hypervisor? So they made a radical choice. They didn't just strip down QEMU, they wrote their own user space virtual machine monitor from scratch to replace it.
Wow. So they threw out the standard component and built their own simpler one.
Exactly. And the research outlines what they call their 7 pillars of hardening for their KVM stack. A few of them really stand out to me.
What are they?
The first one is proactive vulnerability search. Google has dedicated teams of elite security researchers, hackers, basically, whose only job is to try and break their own hypervisor stack.
So they're red teaming themselves constantly.
Constantly. The paper mentioned they found and fixed 9 critical vulnerabilities in the upstream KVM code before the broader open source community even knew they existed. They are their own harshest critics.
Iron sharpens iron.
That's the idea. The second pillar is that reduced attack surface we just talked about, getting rid of all those legacy drivers, no mouse drivers, no floppy disks. And another one I found really interesting was code provenance.
What does that mean?
It means they track every single binary running in their fleet with cryptographic certainty. They know exactly which source code produced it, who reviewed it, how it was built, and how it was deployed. It ensures that what's running in production is exactly what was audited and approved with no chance of tampering.
That's a strong supply chain security story. Now let's get to the hardware. Google has the Titan chip. How does this compare to the Nitro security chip? Is it a similar idea?
Conceptually, it is very similar. Titan is Google's custom-designed security chip. It's a hardware root of trust. It sits on the motherboard, and it interposes between the main CPU and the boot flash.
So it also validates the firmware signature before the machine is allowed to wake up.
Exactly. It establishes that fundamental root of trust in the hardware. But what's really interesting when you read Google's material is their obsession with the physical supply chain. They talk a lot about how they track the Titan chip from the silicon foundry all the way to its final installation in a data center rack to ensure nobody could have physically tampered with it in transit.
That's taking security to a whole other level.
Yeah.
And what about titanium? It sounds like it should be a superhero's armor.
It is effectively Google's answer to the AWS Nitro system. It's their next-generation architecture for offloading virtualization services from the CPU to dedicated hardware.
So we're seeing the same pattern again.
The same pattern.
Okay.
They have the titanium adapter, which is their smart NATU, and within that they have titanium offload processors. They call them TOPs.
TOPs, I like it.
Me too. And these TOPs handle the heavy lifting for crypto, for I/O, for security processing. Again, the goal is to get that messy infrastructure work away from the customer's CPU.
The research also mentions a partnership here, which is a bit different from AWS's in-house approach.
That's a great point. Google collaborated very closely with Intel to co-develop a chip that Intel now sells as the IPU E2000, but it was originally codenamed Mount Evans. This shows that Google is willing to partner with major silicon vendors to build these components, whereas AWS, with Annapurna Labs, tends to want to control the entire stack vertically.
A slightly different business strategy. I want to shift to networking because the research on Google's stack mentions something called Andromeda. That just sounds massive.
Andromeda is Google's software-defined networking, or SDN, stack, and it is a beast. It's fascinating because of how they achieve incredible speeds. They use a technique they call the hoverboard model.
Hoverboard, like from Back to the Future, are we going to see flying skateboards in the data center?
Not quite.
Yeah.
But the idea is that in traditional networking, you have these choke points, these gateways that have to process all the rules. The hoverboard model allows them to distribute the programming of network flow rules across the entire fleet without creating those bottlenecks. But the real speed boost, the truly innovative part, comes from something they call hypervisor bypass.
Bypass. Okay, usually in security, when I hear the word bypass, I get very, very nervous.
It sounds scary, I know, but in this context, it's a brilliant performance feature. With Andromeda 2.1, once a network connection is established and all the security policies are checked by the hypervisor, they allow the guest VM to talk directly to the software switch running on the host via a shared memory region.
So it bypasses the hypervisor thread for every single packet.
It completely skips the middleman.
Yeah.
The hypervisor sets up the secure connection, validates it, but once the data is actually flowing, it just gets out of the way.
It's like a traffic cop who checks your license and registration once, then just waves you through the intersection for the rest of the day instead of stopping you every single time.
That's a great analogy.
Yeah.
And the performance impact is huge. They claim it reduces network latency by about 40%.
40% is a massive number. Okay, before we move on from Google to Azure, we have to touch on Gvisor. This seems to be their solution for secure containers, analogous to AWS's Firecracker, but it sounds very different.
It serves a very similar purpose-isolating, untrusted containerized code, but it uses a totally different and fascinating mechanism. Firecracker, remember, is a micro VM. It's a real, albeit tiny, virtual machine. Gvisor is not a VM. It's what they call an application kernel, written in the Go language.
An application kernel. Unpack that for me. What on earth is that?
Think of it as a fake Linux kernel that runs as a regular program in user space.
A fake kernel.
Yes. When a container that's running inside the gvisor sandbox tries to make a system call or request to the operating system, like open this file or create a network connection, it doesn't actually talk to the real Linux kernel on the host machine.
Where does the call go?
It gets intercepted by gvisor. And gvisor pretends to be the kernel. It looks at the system call, it sanitizes it, it checks it against a strict security policy, and then it handles the request on behalf of the container.
So it's an intermediary that filters all communication between the container and the real host kernel.
It provides this massive security boundary. The container can never directly attack the host kernel's system call interface, which is historically where a lot of container escape vulnerabilities have been found.
What's the trade-off? It sounds too good to be true.
The trade-off is a slight performance overhead, particularly for applications that make a lot of system calls, because of that extra interception layer. But for the massive security gain it provides, it's a fantastic piece of engineering.
So to summarize the two approaches, AWS uses Rust and tiny hardware-assisted micro-VMs. Google uses Go and this user space fake application kernel.
That's a fascinating philosophical divergence.
It really is two brilliant teams looking at the same problem. How do we securely isolate untrusted code? And coming up with two completely different but equally valid solutions.
All right, let's bring in our third and final contender, Microsoft Azure. Now, Microsoft's legacy is obviously very different. They come from the world of Windows. How does that heritage shape their cloud architecture? It shapes it profoundly. At its core, Azure is built on Hyper-V. And unlike KVM, which is fundamentally a part of the Linux kernel, Hyper-V is Microsoft's own Type 1 hypervisor with deep roots in the Windows ecosystem.
And Type 1 just means it runs directly on the bare metal hardware, not on top of another OS.
Correct. And the Hyper-V architecture is defined by what it calls partitions. You have the root partition, which is the host operating system, essentially a stripped-down, hardened version of Windows Server Core. And then you have the child partitions, which are the guest VMs that customers run.
The research talks a lot about something called enlightened I/O in the context of Hyper-V. That sounds very spiritual.
It does, doesn't it? Like your I/O requests have reached a state of nirvana.
So what is it, really?
It's actually a very practical and clever performance optimization. In the very old days of virtualization, a guest VM didn't know it was a VM. It would try to talk what it thought was a physical disk controller, and the hypervisor would have to intercept that and lie to it, emulating the real hardware. That emulation is very slow.
It's a lot of overhead.
A ton. Enlightened simply means the guest operating system knows it's virtualized. It's self-aware.
So it doesn't need to be tricked.
Exactly. Instead of talking to fake emulated hardware, it uses a very high-speed direct communication channel called the VM bus to talk straight to the hypervisor and the root partition. It bypasses all that clunky legacy device emulation, making it much, much more efficient.
Okay, that makes sense. Now, let's talk hardware. We know AWS has its Nitro cards, which are custom ASICs. We know Google has Titanium. What is Microsoft's answer to hardware offload?
This is where Microsoft's journey has been really unique and different from the other two. Initially, they bet very big on a different kind of chip, FPGAs.
Field Programmable Gate Arrays.
That's them. For those who don't know, FPGAs are these incredible chips that you can reprogram in the field after they've been manufactured.
So they're not fixed function like a normal chip?
Exactly. They started this with a project called Project Catapult. They began by putting FPGAs in their servers to accelerate Bing search indexing, and then they had a light bulb moment and realized, hey, we can use these programmable chips for networking and storage offload in Azure too.
Why FPGAs? Why not jump straight to custom ASICs like AWS did with Annapurna?
The answer is flexibility. The cloud landscape moves incredibly fast. New networking protocols emerge, encryption standards change. If you design and manufacture a custom ASIC, its logic is literally baked into the silicon. If you want to change it, you have to spin a whole new chip, which can take years and tens of millions of dollars.
But with an FPGA,
you just push a new configuration file, a new bit stream, and you have effectively rewired the hardware on the fly. It gave them a reconfigurable cloud.
That's a very powerful concept. It's like having hardware that's as updatable as software.
It is. However, the latest research shows they are now evolving their strategy. The modern iteration of this is called Azure Boost, and it's moving more towards a system-on-chip model, much more like Nitro. A key part of this is the MANA.
M&A.
The Microsoft Azure Network Adapter. This is their new custom NIC. It can provide up to 200 GBPs of networking. But the key thing about M&A is that it's designed to provide a stable, consistent driver interface to the guest VM.
So the VM doesn't care what the underlying physical hardware is.
Exactly. The hardware can change over time. It could be an FPGA today, a custom ASIC tomorrow, but the VM's driver doesn't need to be updated. It completely abstracts the underlying hardware evolution.
Very clever. And what about their security chip? Did they have a hardware root of trust, like Titan or the Nitro security chip?
They do. It's called Project Cerberus.
Another name from Greek mythology. I'm sensing a theme in the industry.
There is definitely a theme. Cerberus is Microsoft's implementation of a hardware root of trust. It's compliant with the NIST 800-193 standard for platform firmware resiliency and does the same job. It sits on the motherboard and protects the integrity of all the firmware, ensuring it hasn't been tampered with before boot.
I want to pivot to a really specific but crucial technical detail I found in the Azure research. It's about scheduling. The research talks about a major shift from a classic scheduler to a core scheduler, specifically because of CPU vulnerabilities like Spectre and Meltdown. Can we explain that? Because Spectre was a monumental wake-up call for our industry.
Oh, this is absolutely critical, and it shows how these providers have to react to threats at the deepest level of the silicon. So modern CPUs have a feature called symmetric multithreading, or SMT. Intel calls it hyperthreading.
Right. It lets one physical CPU core run two independent threads at the same time, basically pretending to be two cores to get more work done.
Exactly. Now, the classic scheduler in Hyper-V would just treat these two threads as two independent processors. It would just grab any available thread for any VM. So you could easily end up in a situation where thread A, belonging to customer X, and thread B, belonging to customer Y, are running on the exact same physical core at the exact same nanosecond.
And the Spectre vulnerability showed us that two threads sharing a physical core can potentially spy on each other's data through side channels.
Precisely. They share low-level components, like the L1 cache and execution units. A clever attacker running on one thread could analyze the timing of cache hits and misses to infer data from the other thread running on the same core. It's a side channel attack. So Microsoft and the other providers too switched to what they call the core scheduler.
And how does the core scheduler fix this problem?
The core scheduler has one simple, unbreakable rule. A single physical core is never shared between two different customers at the same time. If customer X's VM needs a thread on a core, it gets assigned both SMT threads on that physical core. Or the second thread is simply left idle. It is never given to another customer.
So they are intentionally sacrificing some potential performance and density for a huge gain in security. They're leaving compute power on the table to be safe.
Yes. It's a deliberate trade-off, but it completely kills an entire class of side-channel attacks like L1TF, also known as foreshadow. It's a necessary price to pay for security in the post-Spectre world.
That's a great example of the invisible work these providers do. Okay, last point on Azure before we compare them all. Confidential computing. The research suggests this is a massive area of investment for them.
It absolutely is. Azure is arguably one of the leaders here. They are investing heavily in trusted execution environments, or TEEs. The fundamental problem they're trying to solve is protecting data in use.
We've gotten really good at encrypting data at rest on disk and data in transit over the network.
Right. But what about when that data is loaded into RAM and is actively being processed by the CPU? At that moment, it's usually unencrypted.
So if an attacker or even a rogue cloud employee could dump the server's RAM, they could see all the secrets.
That's the risk. Confidential computing aims to keep the memory encrypted, even while it's being processed by the CPU. Azure has deep support for technologies like Intel SGX, Intel TDX, and AMD SCV SNP that enable this. But the really cool piece of engineering here from a virtualization perspective is a project called OpenHCL.
OpenHCL? What's that?
It stands for Open Host Compatibility Layer. And get this, it's a hypervisor, a tiny, minimal hypervisor that runs inside the confidential VM itself.
Wait, a hypervisor running inside a virtual machine? That sounds like the movie Inception?
It is a bit like that. And guess what language it's written in?
Let me guess. Rust.
Written in Rust, of course, for memory safety. Its job is to handle device emulation securely inside the encrypted boundary. Because the main Azure hypervisor on the host is not allowed to see inside the encrypted memory of the confidential VM, that VM needs its own little trusted helper to manage virtual devices. OpenHCL does that job.
That is just mind-bending. The main hypervisor is effectively locked out of its own guest VM. It's blind.
That is the entire promise of confidential computing.
Yeah.
Not even Microsoft, as the cloud provider, can see what's happening inside that encrypted VM.
Okay. Wow. We have covered a huge amount of ground. We've got AWS Nitro, Google Titanium, and Azure Boost. Let's put them head to head. Let's do a deep dive comparative analysis. What are the big philosophical differences you see between them?
All right, let's break it down.
First, let's compare the hypervisor base. Where did they start from?
Okay. AWS and Google have both bet on modified KVM. They're coming from and sticking to their deep Linux roots. Azure, on the other hand, is all in on Hyper-V, which comes from its Windows heritage.
So different family trees.
Different family trees. But what's so fascinating is that they have all converged on the exact same idea. Strip the hypervisor down to its absolute bare minimum and move all the complex logic into dedicated hardware.
Okay, next comparison point, their hardware strategy.
This is where we see some real divergence. AWS, with Nitro, is all about their in-house, custom ASICs from Annapurna Labs. They are very mature here, they've been doing it the longest, and their no operator access philosophy is a core foundational tenet of their design.
And Google.
Google, with Titanium, is more of a hybrid. They have their own custom silicon like the Titan chip, but they also partner closely with industry giants like Intel on projects like Mount Evans. Their big focus seems to be on that verifiable supply chain security for the hardware.
And Azure.
Azure, with Boost, has that unique legacy with FPGAs. They initially prioritized programmability and flexibility over raw performance. Now they're moving towards ASICs with Mana, but that history of reconfigurable hardware gives them a different DNA. They can iterate on hardware design very quickly.
This next one is my favorite comparison point, the choice of security language.
It feels like a tectonic shift in the industry, doesn't it? It's the beginning of the end for C and C++ in these critical security components.
Let's list them off. AWS Firecracker.
Written in Rust.
Azure's OpenHCL Hypervisor for confidential computing.
Also written in Rust.
Google's gvisor for container security.
Written in Go.
So we have Rust, and Go. What's the significance of this?
It's a collective admission by the entire industry that memory safety is not something we can leave to chance anymore. For 30 years, hypervisors and kernels were written in C, and for 30 years we've been fighting an endless war against buffer overflow and memory corruption vulnerabilities.
And these new languages stop those bugs at the source.
They make those entire classes of attacks impossible by design. The industry has decided we're done with that. If you are building a new security-critical virtualization component today, you're using a memory-safe language. Full stop.
Okay, final comparison. Their approach to confidential computing.
Another area with different philosophies. AWS offers Nitro enclaves. Their approach is to have you, the developer, explicitly carve out a separate, heavily isolated environment for your most sensitive code and data, which runs alongside your main EC2 instance.
So you have to architect your application specifically for it?
You do. It's more work, but gives you very fine-grained control. Google and Azure, on the other hand, are pushing confidential VMs. Their pitch is more about ease of use. You don't need to rewrite your app. Just check this box when you launch the VM and the whole thing will be encrypted.
So AWS wants you to consciously build a fortress for your secrets, while Azure and Google are trying to wrap an invisible fortress around your entire existing application.
That is a fantastic way to summarize the difference. One is explicit and architectural. The other is transparent and infrastructural.
So let's bring this all home. Let's connect it all back to you, our listener. If I'm a CISO, if I'm a cloud architect, or even just a curious developer, so what? Why does any of this deep architectural detail matter to my day job?
It matters more than ever. Because you aren't just buying compute or storage anymore. You are buying a very specific and very opinionated security architecture.
It's not a commodity.
It is not a commodity when it comes to trust. If you work in finance or healthcare and you have a compliance requirement that states the cloud provider must not, under any circumstances, have access to our encryption keys.
You need to be able to prove that.
You need to understand how the Nitro security chip, or Google's Titan chip, technically and physically enforces that. You can't just take a marketing document's word for it. You need to be able to point to the architecture and say, there's a physical hardware barrier here, or the memory is encrypted with a key the hypervisor never has access to.
It's about moving from trusting the provider's policies to verifying their technology.
Exactly. And it's also about understanding the threats they are mitigating on your behalf. We mentioned Rowhammer.
Yeah, the attack where you can flip bits in RAM just by accessing adjacent memory cells over and over.
All three of these providers are using special ECC memory and are tuning memory refresh rates in hardware to make that attack practically impossible on their platforms. They're implementing the core scheduler to stop CPU side-channel attacks. They are doing the incredibly hard, low-level engineering so you don't have to worry about patching your server's hardware.
But, and I feel like this is where we get to the really interesting conclusion, there is a trade-off in all of this, isn't there?
There is. And this is the final provocative thought I'd like to leave everyone with to mull over.
Go on.
We are rapidly moving toward a world where the hypervisor practically disappears. It's not a piece of software you interact with anymore. It's becoming firmware. It's locked down. It's formally verified. It's immutable. AWS makes the bold claim, no operator access.
Which, from a security perspective, sounds like the ultimate goal. It sounds fantastic.
It is fantastic for security.
Oh.
But let's play this out. If the cloud provider intentionally and provably locks themselves out of your server, what happens when things go horribly wrong?
What do you mean?
If your application has a massive, unexplainable crash, a Heisenbug that you can't reproduce, and you file a critical support ticket, and the provider's engineers come back and say, we're sorry, but we literally cannot look at the memory dump from the host. We cannot log in to the physical machine to debug the kernel state. Our security model forbids it.
We are trading supportability for security.
We are trading the ability for a human to intervene and debug for the guarantee that no human can intervene and breach security. We are locking the door and throwing away the key. And we just have to trust that the automation and the architecture work perfectly.
That is a chilling thought. Is that a trade-off you, as a customer, are ready to make?
For most workloads, especially sensitive ones, the answer is increasingly yes. But it fundamentally changes the relationship you have with your infrastructure. In a strange way, you're more on your own in that locked box than you were before.
Wow. From the virtualization tax all the way to the invisible hypervisor and the supportability trade-off, what a journey.
It's just an amazing time to be working in infrastructure. The rate of innovation at this foundational level is just staggering to watch.
It certainly is. And I feel like we could talk about this for another hour, but that's probably all the time we have for this deep dive.
A fascinating topic.
Thanks for tuning in to InfoSec Bytes. Please keep exploring our 100-plus episodes on information security, AI, cloud, quantum, and cybersecurity incident root cause analysis.
We really appreciate you joining us for these conversations.
And please, like, subscribe. We are on various platforms like Spotify, Apple Podcasts, YouTube, and Amazon Music, and share this with a colleague. It helps us keep the conversation going.
And helps everyone keep their cyber defenses strong.
See you in the next episode, and stay tuned.